In the field of artificial intelligence, particularly with neural language models, understanding how these models make decisions is crucial. This is where mechanistic interpretability comes in. It's a set of techniques aimed at dissecting the inner workings of these models to reveal the causal pathways or specific variables that drive their behavior. However, comparing different mechanistic interpretability methods has been challenging because evaluations are often ad hoc and not standardized. That's where the MIB benchmark enters the picture. MIB, or Mechanistic Interpretability Benchmark, is designed to provide a reliable way to assess and compare these methods across a variety of tasks and models. Created by a team of researchers from institutions like Northeastern University, Technion, and others, MIB focuses on two main tracks: circuit localization and causal variable localization. These tracks evaluate how well methods can identify and validate the key components in a neural network that are responsible for specific behaviors. Let's break down the circuit localization track first. This track is all about pinpointing the exact parts of the model, such as neurons, edges, or connections, that are most important for a given task. For example, imagine a language model performing arithmetic, like adding numbers. The method needs to locate the circuit or pathway in the model that handles carrying over digits or processing tens and ones places. Techniques like attribution patching or analyzing information flow routes are tested here. The goal is to see which methods can most accurately and concisely recover these causal pathways. To evaluate this, MIB uses standardized datasets with fixed inputs and counterfactual examples. This means researchers provide prompts, like 12 plus 9 equals, and then intervene in the model to test if the identified circuit truly controls the output. Metrics play a big role here. One key metric is the area under the curve for faithfulness, which measures how well the located circuit matches the model's actual behavior. They also compute scores based on how precisely the method identifies the relevant edges or components, often using something called F+ faithfulness scores. In their experiments, attribution and mask optimization methods came out on top, showing they can reliably locate these circuits across different model sizes. Shifting to the causal variable localization track, this one dives deeper into the model's hidden representations. Here, the focus is on featurizing a hidden vector, essentially breaking it down into meaningful features, and then locating specific causal variables that relate to the task. For instance, methods might use sparse autoencoders or distributed alignment search to identify features that correspond to concepts like carrying the 1-inch in addition or other high-level variables in a causal model. In this track, MIB compares how well these featurized features align with known causal variables. They use metrics like alignment scores to check if the features accurately represent the variable's role in the model's decision-making. The process involves training or applying these methods on models and then validating them against a ground truth from a high-level causal model. From their findings, supervised methods like distributed alignment search performed the best, effectively locating these variables. On the other hand, sparse autoencoders didn't show much improvement over simply using the standard neurons in the hidden vectors, suggesting that not all featurization techniques are equally effective. MIB isn't just about these two tracks. It's built on a foundation of principled evaluation. The benchmark includes a suite of 5 models and 4 tasks, ensuring that methods are tested in diverse scenarios. This standardization helps avoid the pitfalls of previous work, where comparisons were limited to specific classes of methods or narrow tasks. By using fixed counterfactual inputs for interventions, MIB ensures that evaluations are reproducible and focused on causal validation, which is a core differentiator of mechanistic interpretability from other forms of model analysis. One of the innovative aspects is the introduction of novel metrics, like the faithfulness metrics I mentioned, which provide a more nuanced way to measure success. For circuit localization, they look at things like the area under the curve to account for different circuit sizes, while for causal variable localization, they emphasize precise alignment with predefined variables. This approach encourages the development of methods that are both precise and concise, avoiding overly complex explanations that might not hold up under scrutiny. In their results, the benchmark revealed some surprising insights. For circuit localization, traditional methods like attribution patching held their ground, indicating that while new techniques are emerging, the fundamentals are still strong. For causal variable localization, the superiority of supervised distributed alignment search highlights the value of incorporating guidance from known causal models, whereas unsupervised methods like sparse autoencoders need further refinement. Overall, MIB serves as a claim for what matters in mechanistic interpretability: the ability to locate and validate causal elements in neural networks. By offering public leaderboards where researchers can submit their methods for evaluation on private test sets, MIB fosters competition and collaboration. This setup not only increases confidence in new advancements but also pushes the field toward more meaningful progress. Researchers can use MIB to test their innovations against a stable standard, ensuring that comparisons are fair and insights are generalizable across models and tasks. As language models grow more complex, benchmarks like this are essential for building trust and understanding. They help us move beyond black box AI toward models that we can explain and control more effectively, paving the way for safer and more reliable applications in real-world scenarios.